All right, so this is going to be your video on chapter 22 and 23, current and circuits. I am going to include timestamps in the description of the video down below so that you guys can go back and select which part of this, very long, week-long series of lectures that we've done so far on electrical currents and circuits and how they interact with one another and how they relate to things that we've already talked about in terms of electrostatics, the moving electrons and those sorts of pieces, as well as obviously the new content. So I'm going to move a little bit more quickly through this than I did in class. Not because I don't think everything we talked about in class was important in class, I just used a lot more examples. And I'm going to continue using those examples in class. So this is going to be as quick and efficient as I can get it. Remember that you can also find all of these notes on the Teams page in the Unit 11 file tab. So as we begin, here we go. The first thing we need to talk about is electrical current. Electrical current is described in a few slightly different ways. Electrical current primarily is the movement of what we now understand to be electrons. That wasn't always the case, so most standard definitions that you will read in many different sources are going to say that electrical current is the flow of charged particles, because for about 150 years, that's what we thought they were. Benjamin Franklin had this understanding back in the day where he's running through lightning storms with kites, and we understood at that point that there were oppositely charged things, like charges repel one another, opposite charges attract one another, and we labeled those as positives and negatives because those are the two most polar opposite things we could name them. He flipped a coin and he guessed that they might be positive charges that are moving from location to location. And for a long time, that's what every physics textbook, lecture, and diagram represented. I bring this up because we refer to it as conventional current. That's what you see at the bottom of the screen, right? We call this conventional current because that was what we described as current for a long time, more time than we have understood and known what the electron was. So I bring this up because you are going to see some diagrams. I've tried to get rid of as many of them as I could throughout the course of these last, throughout the course of these last couple of years. I've tried to get rid of as many of those as I can. But primarily the way you'll see this represented is that in a battery, you've got a positive terminal and a negative terminal. And every diagram I'm going to use is going to show electrons leaving leaving the negative terminal of that battery. It's freaking out on me. Anyways, electrons leaving the negative terminal of that battery and going through the circuit. And as they leave the negative terminal of the battery and go through the circuit, through the light bulb, they return in the positive terminal because that's what we recognize that they actually do now. We know that these electrons are the things that are actually moving. But for the vast majority of our understanding of electrostatics or electrical current, we actually thought it was the other way around. All because Ben guessed wrong, and that was really it. So I bring this up because you might see one diagram that shows positive charges moving or charges leaving the positive end of a battery. We understand that that is incorrect now. But for a long time, we didn't know even what an electron, a proton, a neutron, or the nucleus of an atom was. We had no idea what was inside of an atom. And that's where that misunderstanding comes from. So in all of my details, and all of my descriptions, and all of my diagrams, throughout the remainder of the year, I'm using the direction electrons move. I will always talk about electrons leaving the negative terminal of the battery, moving through the circuit, and returning to the positive terminal of the battery because opposites attract. The electrons are going from negative to positive. And that's what is actually happening these days. But understand that there might be some diagrams snuck in there or from other sources that you decide to go, right? Crash Course Physics is a great YouTube series. Khan Academy is a great YouTube series. And I'm not sure what it is they use in terms of their descriptions of electrical current or the way that these charges might move. So you might see both. It is the electron. Now, a circuit itself is just going to be any sort of closed loop where those electrons or those charges move from one location to another. It has to be a closed loop. If there is if there's an opening in that loop in any way, shape, or form, then the electricity is going to stop completely. It's what happens when you turn off a light switch. It's what happens when you drop your phone and it breaks. It just won't even power on. One of the circuits somewhere in there got disconnected. And now the electricity can't move from location to location. Now, the cool thing about this, that second bullet point, is that These electrons in your circuits follow the exact same rules and patterns that everything else has. Just like a ball rolling down a hill going from high gravitational potential to low gravitational potential, or wind on a weather map going from a high pressure region to a low pressure region, or heat on a stove going from a region of high temperature to a region of cool temperature. All of these things are the same pattern that we see with electrons. They go from regions of high concentrations of electrons, high negative charges, to regions of low concentrations of negative charges, where the positive terminals are. And they always go from these high concentrations to low concentrations. If that is starting to sound redundant, because that's something we've talked about in every unit we've talked about so far, good. It's the second law of thermodynamics, and it pops up everywhere. We're not going to get into thermodynamics, don't worry, but that's why it is always there. In electricity, you've got, instead of calling it a high pressure region or a low pressure region, instead of calling it a high gravitational potential energy or low gravitational potential energy, or high heat or low heat, we will refer to it as electric potential. It is the potential that those electrons have to affect change in the world around them, right? That electric potential can be used to do work. It can supply energy. If we're calculating how that energy changes over time, then we can talk about the amount of power that these electrons can deliver for us and do for us. And that's the unit that we refer to as voltage. I like to think of electric potential literally as the best analogy. It's not truly what it is, but the best analogy is the height of a mountain. The electrons in these circuits are skiers going down the mountain. The taller the mountain, the more electric potential they have, the more work gravity will do on the skier as it pulls them down the mountain. The faster the skier will be going, the more the electrons can do, the higher the electric potential, the higher the voltage. That's my best analogy for it. I'll come back to it quite a bit. This is also a great just picture, right? There's no really notes that you need to put here. This is all just a description of what's going on in that little photo. But again, the water flowing from high gravitational potential to low gravitational potential and spinning that little water wheel that is in there doing work for us. That's what we're doing. As the electrons go from high electric potential to low electric potential, we use their energy that they have, and we use that to do things for us. Power light bulbs, spin a fan, turn another electric motor, maybe for an electric car, or produce heat, produce sound. Whatever other form of energy we need, we take that electrical energy and convert it into that other form of energy. Electrical current, because this is physics, of course we can do this. Electrical current is the rate at which this current is flowing. We measure this in a unit referred to as amperes. It is named after one of the scientists in the mid-18th century, 1800s. I think technically it's the 19th century. That one always was weird. Doesn't matter. It's named after the guy. We use the capital letter I as its symbol. Don't ask me why we do that. I wasn't at the meeting where we established that that's what we're going to use, but that's what every physics textbook I've ever seen uses. Because we're calculating the rate at which charges flow, anytime you say you're calculating the rate of something, it is your change over time. And so this is literally just the amount of charge that that object has divided by the time that it took for that charge to move. The unit that we use for calculating in ampere, or the units, because it's charge divided by time, it's a coulomb per second. So those units from last couple, this is going to be confusing. Let me rephrase it. Those units from earlier parts of the year for time and for charge still hold. Now, if identifying what variables we're using when I give you things in a word problem has historically been difficult for some of us. In the last exam, I think that was the biggest hurdle. Either we knew exactly how to label our variables and we didn't have issues or concerns with picking the variables or picking the equations. We typically did pretty well in the written portion. If we didn't know what those units on those numbers meant, then we weren't able to adequately identify what variable it was or pick the right equation. That, in my opinion, is always the first and usually the biggest hurdle in the electrostatics or electrical current units. So if you need to do this for all of the equations on the cover page, please do so. This is a fantastic idea, making sure you've got somewhere, even if it's just a scratch sheet of paper that you have next to all of your homework assignments as you're doing the remainder of the work in this unit. It's a great thing to have. That way you can practice it while you're doing all of the homework problems, which are literally just meant to be practice. It's why I give you the answers to them before you even begin the assignments. But I think this is a fantastic idea. So There's nothing you need to write down in these next couple of slides. All I'm doing here is being annoying, as I'm sure some of you guys think I am. I don't like... Historically, students, if they don't know what they're doing or get panicked or confused, concerned, whatever, oftentimes the first thing I'll see them start doing is just multiplying or dividing the numbers that are there. And I want to emphasize why it's so important that we multiply when we're supposed to multiply and divide when we're supposed to divide. This is why I give you the equation card. You can have all these equations on there. We don't arbitrarily choose to multiply or divide these things. These equations get rearranged and shuffled around based on the same basic rules of algebra you talked about freshman year. So in the top equation that we've got here, this equation for electric potential difference, being work divided by charge, the amount of work required to move that charge in the denominator, was an equation that we used in our last unit. So all I've done is multiply both sides by Q here in order to rearrange my equation and get an equation that solved for work. And then remember the work energy theorem. Work and energy are synonymous with one another. Work is the amount of energy change. So we can still use this equation to calculate how much energy one of these electrons might have as they're moving through the circuit. And that's fantastic. We can use this a lot in everything that we're going to be doing. I don't expect you to ever have to do any of these proofs or rearrange these equations in the way that I'm about to. This is my way of showing you where the equations that we use come from and why it's so important that we multiply when I ask you to multiply or divide when the equation says to divide, why we square this variable and we don't square that variable. This is where they come from. Again, this is something you're not going to have to do again in class. This is just where the equations come from so we can be on the same page. All I did here for my power equation, recognizing that power is energy change divided by time, usually work divided by time, but we replace it with energy. And I'm taking two variables that I could also multiply together to get that value of energy from the previous slide, and I'm substituting them where that energy term was. And then in the next line, I'm doing the same thing with Q. I can replace this value for Q for the two things that I rearranged in my charge equation, or my current equation that we started this slide with, or sets of slides with, and replace them. And all I've done is a little bit of substitution. Now, it looks like things got a lot more complicated, but remember what happens when we have something divided by itself. You can cross those out, right? Those units, those variables, whatever it might be, they cancel. And when we reduce all of this, we get the power equation that we honestly are using for the vast majority of assignment 3. And this power equation is incredibly useful. It's power being equal to the rate at which those electrons are moving, the capital letter I, that's our current, multiplied by the electric potential that each one of those individual electrons have. And this is our relationship that we're able to use. We're not dividing because the substitution that we did left both current and voltage, electric potential, in the numerator. We didn't get rid of the value for time because I don't like time. It's passing too quickly, I'm getting old, whatever. It's not the reason. We got rid of time because it canceled. Now, why it's not there, not really all that important, but if you know P equals I multiplied by V and you don't ever add, subtract, or divide those two values, we're good to go. That's the point. I've got a couple of practice problems here that I wanted you guys to try. This was part of assignment 1. It's the very first page, very first set of pages, very first assignment in your Unit 11 packet. Here's all the work for it. If you've got questions, comments, or concerns, don't hesitate to ask. I do want you to try it at some point as you're studying for the exam so that you can see whether or not we're on the same page in terms of our ability to identify variables. That's the crucial step. So moving on from there, we have to talk about two different kinds of electrical current because not all electrical current is created equally. There are different styles or different ways in which we can send electrons from point A to point B. We have direct current, in which those electrons are only allowed to move in one direction through the entire circuit, and one electron has to make the whole lap. As a track coach, my best analogy for this, and if you're not familiar with track and field in class, I use several more analogies. My best analogy for this is running a mile. If you're running a mile in an event in track and field, the 1,600 meter run, it's a little less than a mile. That's not important. If you're running a mile in track and field, you have to make 4 laps around the track as fast as you can. It is you and you alone making those 4 laps around the track as quick as you can. Alternating current is different. Those electrons are able to move back and forth. A single electron in alternating current does not need to make the entire trip through the circuit. A single electron in alternating current does not need to make its trip all the way around the track 4 times. So direct current is like running a mile all by yourself, and alternating current is like running the 4x4. The 4x4, for those of you who don't know, is 4 people running 400 meters individually. At the end of that race, right, one person runs 1 lap, 400 meters, hands off a baton. The next person runs 1 lap, 400 meters, all by themselves, passes off the baton. And you do that 4 times. And at the end of the race, collectively, you have run 1 mile. So direct current is the one person doing 4 laps all by themselves. Alternating current is 4 people, each running 1 lap, passing the baton off in between. The baton makes 4 laps, but each individual person, each individual electron does not need to make the full 4 laps. This is the best analogy I can come up with for direct versus alternating current. The baton in the alternating current example is the energy that those electrons have. It's being passed from electron to electron to electron, like dominoes knocking one over another. The energy travels from one point in the room to the other point in the room. The single domino doesn't. Just like one runner does not make the 4 laps. That's the difference between the two. Now, one is more advantageous than the other. We're going to talk about those advantages and disadvantages. What I do have is a little bit of history, and we're not going to get into a whole lot of the history right off the bat. I'm going to gloss over these slides. This is one of my favorite just drama-filled bits of history in terms of scientists, and it's Edison and Tesla and the fight between them. Edison was primarily known as the father of electronics, modern electronics, because he filed patents for over 1,000 different electronics or electrical components. Now, I know he didn't invent the telephone or the telegraph, right? That was, what was his name, Bell? But the components that were used to build those first telephones were definitely things that Edison held a patent for. He made a lot of money off of all of these different patents. The light bulb is probably the one you're most familiar with. Now, there is a downside. I say these are allegations because I'm pretty sure he settled out of court on a lot of these claims, but he was sued quite a bit. He was sued quite a bit by his employees for claiming that he was stealing their research and all sorts of stuff. So a lot of people will say he invented the light bulb. A lot more people will say he stole the light bulb. I can't say one way or another which way it was, but one thing he does get sole credit for is inviting Nikola Tesla to the United States, right? Nikola Tesla emigrated from, I believe it was Serbia, don't quote me on this, I know it's a video, somewhere over there in Eastern Europe, northeast or northwest Asia. But he emigrated from that region and arrived here in the U.S. on a work visa, worked for Thomas Edison in his lab. The two of them didn't get along, primarily because Edison wasn't very well schooled, and Tesla was. Tesla was very good at mathematics. This became an issue because Edison, allegedly, as he would probably try and steal a lot of his employees' research, didn't understand the mathematics Tesla was doing. The big piece of contention here became Edison's entire fortune was built. All of his patents were involving direct current, or most of them, enough of them to where he was concerned. And Tesla's patents that he was beginning to file, the things that he was getting credit for, because Edison didn't have a way of stealing them yet, because Tesla was working theoretically with calculations and equations, and Edison wasn't familiar with those. All of Tesla's pioneering innovation dealt with alternating current. And the two men became the leading scientific figures in these two competing styles of electrical current. Which one is better? This is where the notes resume. Direct current, really easy to make. 9 times out of 10, if you're using an electronic like your computer, a laptop, not a desktop, but your computer, your cell phone, whatever it is you're using to view this video on, if it runs on a battery, it's operating on direct current. Direct current, because that single electron makes the trip, is incredibly difficult to send long distances. What it would have meant, because both Edison and Tesla were fighting over the first contract to power downtown New York City at the time in the early 1900s, 1901, 1902, to go with Edison's style of electricity that all of his fortune was built off of, downtown New York would have needed to build a power generating facility just about every square mile, if not every 2 square miles. And considering downtown New York City was already a bustling metropolitan, area, that wasn't going to be very practical. Alternating current, because a single electron does not make the whole trip, because you're just passing the baton from one electron to the next, it's incredibly easy to send alternating current very, 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 very long distances, which would mean you need significantly fewer power plants. Obviously, downtown New York went with Nikola Tesla and the company he represented, Westinghouse. They went with alternating current to power the walls of downtown New York. Now, this upset Edison because he realized his fortune was disappearing. Obviously, if you haven't noticed, this is where AC/DC got their logo and stuff from, too. It's a lot of fun that way. But Edison realized that he was not going to get a piece of this money, that he was going to continue to lose these contracts to power new cities. And Edison realized that if he could not beat Tesla's technology, which he couldn't, direct current in terms of powering full metropolitan centers was inferior to alternating current. It's just a statement of fact. He began to realize that if he couldn't beat Tesla's technology, he might as well try and beat Tesla. And that's exactly what he did. I'm not going to show the video here, but instead of, just because showing videos in a video usually doesn't work, I'm not that good at editing yet. Maybe one day my YouTube channel will improve. But he began bringing all of these people together to these massive events where he was basically saying, I know the circus is about to put down these animals for X, Y, and Z reasons, whatever reasons they might have been. Let me put the animals down for you. And he did. There's even a Bob's Burgers episode over this called, it was over Topsy the Elephant, and it's a fantastic episode. You should check it out. But the execution of these large circus animals, the elephants and all the other things that he might have done with this alternating current, was his attempt at displaying how dangerous Tesla's alternating current was to the general public. And since Edison was so wealthy, all of the newspaper articles were ad space, all of the flyers on the walls of downtown New York City at the bus stops, all of the pre-silent movie news updates that were in the movie theaters at the time involved Tesla's false campaign trying to tell the world that alternating current was more deadly and dangerous than direct current. That was his sales pitch. If alternating current can murder these massive circus elephants, these massive animals, do you want alternating current in the walls of your home? And because his wealth was so vast, there weren't many people who could compete with him for ad space. And that's what the general population heard. So between that and that very successful smear campaign on Tesla's part, or on Edison's part, attacking Tesla, and the fact that rumor has it that Tesla was also a homosexual man in the early 1900s, he was not in a good place to be in the ire or the crosshairs of the general population. He was being targeted. He was being verbally, potentially physically assaulted in the streets of New York, and he left. He went to Colorado Springs, Colorado, where he worked for the remainder of his life, and he died not sharing any of his technology, any of his inventions, any of his innovations with the rest of the world. He was so paranoid that Edison was going to continue to follow him and try and take his inventions, take his ideas. He recognized that his dream of giving everyone free wireless electricity was so socialist and anti-Thomas Edison and anti-early American capitalism that he invented his own language. To this day, we cannot read Nikola Tesla's notebooks. We don't know what's in them. He very well could have been one of the smartest men to ever live. I think he was one of the smartest men to ever live in the history of our species, and we have no idea what he knew because Edison was so successful in running him out of town. Why do I bring that up? What was the issue with Thomas Edison's electricity? This is what he couldn't beat. This is what Tesla did better than Edison did. Electrons move incredibly fast. We've all turned light switches on and off, and you've seen how quickly lightning or the electricity moves. We've watched lightning storms in our lives, and you can see how fast and rapidly those electrons shoot across the sky. It is impressive and terrifying. Electrons move incredibly quick, but they do not move at the speed of light, despite being a subatomic particle, which should be able to travel very near the speed of light, because there are things in their way. And this is something a lot of people forget. Wires are not like pipes with water flowing through them. Wires are very much solid material. It's made out of solid metal. It's made out of copper atoms or silver atoms or gold atoms or iron atoms or whatever it might be. And there's stuff in the way. And so as those electrons try to pass through, what the majority of an atom is an electron cloud, right? The majority of an atom is empty space. We learned that last year in chemistry, and you have this dense, very positively charged nucleus at the center. So while most of the electrons over a short distance can make it through the electron cloud of the atoms that are inside those metals without interacting with anything, not all of them will. And statistically, the further it goes, the electron, the more likely it is to hit or get too close to the nucleus of an atom and interact with those positive and negative electrostatic charges that we calculated in our last unit. So electrical resistance is something that we can't get rid of. It is a measure of how much current is moving through a circuit, and we can increase and decrease how much current is moving through a circuit. We measure it in ohms, give it the Greek symbol omega. Electrical resistance is something we cannot get rid of, but it's also something that we use to our advantage. Let me explain. The first part is going to be how we can't get rid of it. These are the factors that influence electrical resistance. These 4 factors that we're about to discuss are going to be on the exam, but they're going to be on the exam qualitatively. So I'm going to ask about whether a long wire or a short wire has more or less electrical resistance. That's an example of the sort of question you'll see. We won't calculate it based on the length of the wire. We're not electricians or electrical engineers. We're not going to be doing that. But continuing off of what I was just discussing, the further that electron goes, the more likely it is, the higher the statistical probability becomes that that electron will get too close to a proton of one of those atoms inside the metal and be positively attracted to that nucleus, and instead of moving parallel to the length of the wire in that horizontal direction, whatever it might be, the more likely it is that it interacts with that positive charge and it gets turned, kind of like a comet going around a star or the moon going around the earth, right? It's going to have its path redirected because of that electrostatic attraction that is there. The further the wire is, or the longer the wire is, the further the electron has to go, the more likely that is to happen. And at some point, the electrons will no longer be traveling the direction the wire is moving. They'll be doing this, pinball sort of Plinko style game from The Price is Right, where the electrons are just bouncing back and forth because they've all been redirected. And you're going to have a maximum range of electricity. This is why power lines have such high voltages, is they try to energize those electrons to as high a value as they can so that happens a lot less and you can increase the range of those wires. The next one is referred to as cross-sectional area. If I'm being completely honest, this is a scientist, nerdy, pretentious way of saying diameter. How thick is that wire? That's really all it is. Electrical resistance gets greater the thinner the wire is. These two things are opposites of one another. I would have said inversely proportional, but they are opposites of one another. And the best analogy for this is your road. 355 and I-80 right near us, right? If you're driving on I-80 where 355 is at, it's a nice, neat, brand new-ish, paved 3-lane highway. And in those 3 lanes, you have options. If you get stuck behind a semi, you can go to the next lane. If you get stuck behind grandma on her way to church, going 10 under the speed limit, you can go around her. You have 3 lanes, you have options. There's very little electrical, or in that case, traffic resistance. You have options. If you're on a 1-lane road going through New Lenox or Manhattan during the harvest in the fall and you get stuck behind a tractor, that's a lot of resistance, right? I hope oncoming traffic is not all that intense so that you can get around that tractor, but we've all been in an instance where that isn't the case. The thinner the wire is, the more friction there's going to be between those electrons, the more resistance there's going to be, the fewer options those electrons have for navigating that environment. And so that's the best analogy I've got for that one. Temperature is also another good one. You've all left your phones out on a hot sunny day in the sun, come back and it gives you some sort of temperature warning. It's 2011 right now, or sorry, 2012, 21. Wow, I'm tired. 2021 as of the making of this video, and my PlayStation, that's where I was going, that I bought in like 2011 is a decade old at this point. When I turn on my PS4, it sounds like, after an hour of playing, a jet engine on an airplane trying to take off from the tarmac, right? It sounds like it's going to take off or explode. Now, the fan is gummed up with dust and dirt and all these other things, but the fan is there because it's trying to decrease the temperature of the internal components of the PlayStation, because the higher the temperature gets, the more electrical resistance there will be. The more likely my games are to freeze, lag, or the whole thing is just going to shut down and turn off on me. And so we've all experienced that, at the very least, with our cell phones out in the sun. Right? The higher the temperature, the more electrical resistance there's going to be. And then last but not least, obviously, there's the material. The periodic table, every element on the periodic table is slightly different than another. And there are trends, there are patterns. Obviously, gold, silver, and copper are all in the same vertical column, the same family of the periodic table. They are fantastic conductors. But the electron configuration of each one of those individual atoms on the periodic table is going to influence how well it holds on to or does not hold on to electrons in its valence shells. And since electrons moving through those electron clouds is what electrical current is, every atom's slightly different electron cloud configuration is going to influence that. And this is just going to be a qualitative thing. The main qualitative questions I would ask you on an exam would be about length, cross-sectional area, or temperature. I'm not going to get into materials. We're not going to get into, do you remember what families on the periodic table conduct better? That's going to be it. So those are the 4 factors of things that we can't get rid of. What we can control is how much electrical resistance individual components in the circuit have, and we use this to our benefit. We use this to our benefit because what resistors do is they slow the electrons down, more or less. They use the electrical energy that those electrons had, and they convert it into heat. We use the energy in a resistor that an electron has, and as it goes through the resistor, the electric potential it started that circuit with drops. If there's only one resistor, it'll use all of its electric potential in that one resistor. If there are 5 resistors, it'll split that evenly if it's a series circuit. We'll talk about that later. But this equation right here is referred to as Ohm's law, again, named after the guy. And Ohm's law is our relationship between electrical resistance, electric potential, and electric current. I prefer rewriting it as V equals IR. You'll notice these 2 equations are the same thing. If you wanted to solve for voltage or electric potential, you would multiply both sides by current, by I, and they mean the same thing. I like V equals IR because I don't like fractions, right? Elementary school was rough for Mr. Willis. We've talked about this a lot in class. But it's the same mathematical relationship. And if you actually check out assignment 2, you'll find one of those triangles. If you liked the density triangle from chemistry last year that helped you rearrange the density equation, there's one of those on assignment 2. Assignment 2 is not homework, but it's there for you. These resistors generate heat. Now, electrical current moving through a circuit is going to generate heat anyways, but we intentionally put components in there that we call resistors to generate more heat. Some of them we use explicitly for like toaster ovens or electric stovetops. Some of you guys might notice if you have too many apps running on your cell phone begins to overheat, or my PlayStation begins to overheat and the fan's got to kick on and it sounds like it's going to explode. But those resistors are literally just going to be anything that uses electrical current or uses electrical potential. Sorry, it slows electrical current and it uses electric potential. We use that electric potential to power lights, space heaters, whatever it might be. Yes, I did introduce another proof. No, these steps are things you do not need to know. Again, it is important for me that you know why when I combine these 2 equations in the 2 different ways that I can, I get two different equations. Now I want you to notice, all I did in my green equation is replace voltage for the things that I could use in my blue equation to calculate voltage. All I did here was in my green equation replace electric current for the rearrangement. If I divided both sides by R, that would be my equation for calculating resistance, or sorry, electric current. It's voltage divided by resistance. And then when I simplify them, this is why current gets squared and voltage gets squared and resistance does not. This is why on the left I multiply by resistance and on the right I divide by resistance. I'm not going to ask you to do these proofs in a homework assignment or on a quiz or on a test, but this is why I emphasize the right equation at the right time. So make sure your equation card is updated. Include these two red equations on there, right? Power is equal to current squared multiplied by resistance, and power is equal to voltage squared, or electric potential squared, divided by resistance. The fact that you're dividing in one equation and multiplying by the other is crucial. You have to, because they're different relationships. Not because I felt like, multiplication and division both deserved their moment in the sun. They both deserve their time to shine, their 15 seconds of fame. No, it's because of the way the substitution and reducing the terms worked out. That's how it is. We can also plug this into our energy equations, and you'll notice this is where we get the two different energy equations on the cover page of your packet. I'm not choosing I squared multiplied by R multiplied by T because I don't like fractions. I'm choosing that because that is what the math led to. That's what the substitutions and rearrangements of those variables led me to. That's the important part that I wanted you to see. You don't have to do the proofs. You only need to have the equations that are written in red on your equation card. Once you have that, identify your variables, and it's like picking something off a menu. Which one fits best based on what you've got? That's all it needs to be. Again, more practice problems. Give them a shot. See how you can do. If you've got questions, don't hesitate to ask. I'm actually going to skip this part because it's quick, and we'll do a little bit of it later. It was the last couple on assignment 3 that I told you could skip for now. We'll talk about them the next time I see you. So chapter 23, parts of a circuit. There are going to be 4 main primary components to a circuit that we are going to need to use and take into account when we are drawing our circuit diagrams in assignment 4 and beyond for the remainder of the unit. The voltage source that we're going to use, the battery usually, especially in the lab that we're going to be doing in this unit, is going to have this particular little symbol. The wires that connect all of our electrical components, the pipe that the electrons are traveling through, are represented right here on the battery. And you'll notice the battery, let me see if I can get that thing to pop up down here at the bottom. There it was. Let me change my color. This piece right here, the short line and then the longer line, represent the 2 terminals of your battery. I've made those blue. The 2 terminals of your battery, the positive end of your battery and the negative end of your battery, there's a chemical reaction inside the battery that moves electrons from one side of the battery to the other. They create an imbalance within the battery, an unequal distribution of those charges, which is why batteries don't last forever, right? That can't run forever. It takes energy to keep those electrons on one side versus the other. But when you connect the 2 terminals, the 2 ends of the battery, to a circuit, you give those electrons an out. Right? The chemicals inside the battery will not allow the electrons to move from one side of the battery to the other, but if you open a door on the negative end of the battery and give the electrons a way to move through the circuit back to the positive terminal, they're going to take that route. Because electrons have always wanted to go from high concentrations of electrons to low concentrations of electrons. That was the last unit with electrostatics, and it holds true now. It's why electrons move through circuits. They're going from the negative terminal, where they're highly concentrated and crowded and surrounded by a lot of other electrons. And then they have a door open that allows them to go through a hallway, like a wire, to the positive terminal, where there's a lot more space. There are fewer electrons. A resistor, remember, a resistor is anything that uses electrical potential and slows electric current. That's what I was looking for. These can be anything that you plug into a circuit that uses that energy, right? Light bulbs, toaster, TVs, computers, cell phone displays, sending wireless signals like text messages, whatever. That's a resistor because it uses the electric potential that the electrons have. We usually denote a generic resistor by a little squiggly line. Every now and then, if it's something simple like a light bulb, we'll just draw a light bulb, and you're welcome to do that on the lab that we're about to start. But 9 times out of 10, I mean, it could be a TV, it could be a toaster. I don't know what it is, so I'm just going to draw that little squiggly line to represent a resistor. That's all that is. And then you have your switch. Open and closed switches are the two phrases we use to describe the positions of a switch. You can have a closed circuit or you can have an open circuit, a closed switch or an open switch. Please do not think of switches as doors. That's probably the biggest misconception that a lot of us walk into this unit with. You think of an open door, it lets me walk through, cool, I'm good to go. Things can move if the door is open. But switches aren't like doors. Think of a switch like a bridge. Like a bridge over the Chicago River in downtown Chicago, or any like maybe a drawbridge on a castle with a moat, whatever. I don't know what kind of bridge it is you want to think of. It doesn't matter. If the bridge is down, like it is on the right-hand side, then those electrons can travel from one side of that switch to the other. And the circuit will be powered on, lights will be on, the TV will be on, the cell phone will be on, whatever it is, because the bridge is down, and traffic, the cars, the electrons, can move from one side to the other. If the bridge is up and there is no connection there, those electrons cannot make it from one side of the river to the other. The electrons have to stop. Just like if the bridge is up, the cars cannot pass the bridge, right? We're not Jason Statham or Dwayne "The Rock" Johnson in some high-stakes action movie where we're going to use the bridge as a ramp as it goes up. We're not doing that with the electrons. They don't do that. That's kind of a lie. They can if there's enough potential. You get a spark. It's what spark plugs are. We're not going to get into that. If the bridge is up, the electrons don't go from point A to point B. That's our main idea. Right? And all of that's written right here. So if the switch is closed, like you see in that little guy down there, and the two ends of your brass tabs are making a connection, right? You're going to have wires coming out the bottom of the switch here, wires coming out the bottom of the switch here, and as the electrons travel up and in that little brass tab, they're going to go up and into the lever. And if the lever is making a connection to the other brass tab down here, then they're going to travel down and through the remainder of that wire. And you have the light powered on. If you raise this lever and do not have a connection being made right there, then there is not going to be any ability for those electrons to travel from point A to point B, and the whole circuit stops, right? That is an open switch, no electricity moving, versus a closed switch, where you do have electricity moving. Most electronics, no, not most, that's a lie. Some electronics have the nice little on-off written on there. Most power strips, however, have this ridiculous little symbol with a line and a circle, and we all at some point have flipped frantically back and forth trying to figure out which one is going to power on our TV, because we have no idea what those mean. Remember, we're going back to our original idea of what a switch is. This represents a closed switch where that connection is being made, and so this means on. And this represents an open switch where there is no connection. You raise that lever, and this means that it is off. It's annoying because both on and off start with the letter O, and that letter O down below can be really confusing. I get it. I was confused by it for the longest time too. But that's what those mean. So the solid line, you're making a connection. The O means that it's open. It does not allow for electricity to move through it. I don't know who, someone filed a patent for this. They made a boatload of money. They combine those symbols to give you this. And this is the power button that you see on a lot of electronics these days. I don't know who's making money off of that, but they're probably making a decent amount because it's a pretty clever design. But that's what that symbol represents. It is your on-off switch, and it comes from that bottom right-hand thing that switches back and forth. There are lots of different kinds of circuits that we can have, and we're going to talk about these in a moment. These are going to be as complicated as our circuits are going to get because they can get a lot more complicated, but we are not going to get there, so don't worry about it. So those two main categories of circuits. The first main category of circuits are a series circuit. Series circuits are like a one-lane road in town. I'm sorry, let me be more specific. Not a one-lane road, a town with only one road. There are towns like that where the entire town has driveways that build off of that one road. If you go far enough down LaGrange in between Frankfort and Bourbonnais, in between those two, you'll encounter some town where there's like 15 houses All of them have driveways that extend out to LaGrange, and the speed limit drops from like 55 to 35. And I'm always worried about getting caught by a cop because I forget to slow down. But the series circuit is like that. If there's an accident on that one road, that's the only road for town. You cannot make it from one end of town to the other. Now, town, I think it's got a population of like 60 people. It only like exists in 1/4 mile, like quarter square mile, whatever. It's really small, but that's an example of a series circuit. Another really good example are your really cheap Christmas lights, right? If one bulb goes out and the entire strand of lights go down, that means there's a circuit that, or an opening in the circuit somewhere where that bulb broke, and that one opening prevented electricity from flowing through the entire thing. Those are the really cheap, like $5 Walgreens off-brand Christmas lights, the kind I buy because it is what it is. Parallel circuits are the more expensive versions of Christmas lights that you can buy, where if a single bulb goes out, maybe just that bulb is out. Or if a single bulb goes out, only 3 or 4 bulbs might go out. Those parallel circuits contain multiple paths. Maybe each bulb has its own route from the voltage source to that one bulb and back. Or maybe they put a string of 5 on a circuit, and you get electricity leaving the voltage source going to the first of the 5 bulbs, goes through all 5, stops, and then turns around and comes back to the voltage source. And then there's a separate circuit for the next 5, and it returns to the voltage source, and a separate second circuit for the next 5, and it returns to the voltage source. That is a more complicated circuit to wire. That's what your homes are wired in, which is really good, which is why when you unplug something from the wall, the lights don't turn off, or your refrigerator doesn't stop running, or when a nurse in the ICU at Silver Cross Hospital turns the lights off in a patient's room, the life support does not also turn off. That would be bad. You need multiple circuits so things can work independently of one another. Those are parallel circuits. The calculations for parallel circuits get a little bit more complicated. We will practice them. There will be no less than a dozen practice problems involving parallel circuits, and like 2 on the exam. But you'll definitely also need to know the conceptual differences between them. So this is a really good slide for that. Calculations with it, if you want to calculate the total resistance in a series circuit, it's really easy, because in a series circuit you have to go through, let's say it's a 1-lane road and you've got 5 red lights in town, 1 road for town, you've got to go through all 5 red lights in order to get from one side of town to the other. And so that is a potential source of resistance as you go from one end of town to the other. So the current, resistance, very easy to calculate in a series circuit. Parallel circuits are a little bit more complicated because the electrons, this is where the phrase comes from, will literally try to travel through the path of least resistance. Meaning, if I've got 3 resistors here, R1, R2, and R3, and R1 has a value of, I'm just making things up here, 10 ohms of resistance, R2 is 20 ohms of resistance, and R3 is 30 ohms of resistance. The vast majority of the electrons, when they leave the battery through the negative terminal, come up to junction 7. Statistically, more electrons are going to travel through R1 because it contains less electrical resistance, and then complete this circuit for R1. That's the circuit that the vast majority of these electrons will travel through. You'll have fewer electrons that go through R2, and you'll have the fewest number of electrons that decide to go through R3, because R3 has the most resistance. Now, I'm not saying R3, resistor 3, the 30 ohm resistor, will have no electrical current going through it. Absolutely not. Statistically, some electrons will go through that resistor, but comparatively, it will be significantly less. Significantly. If all 3 of these resistors were identical and they were all 10 ohm resistors, then you're going to wind up with equal current going through each one of those. So because each one of those can have varying amounts of electrical resistance, calculating the current through the circuit can be a little weird. You can calculate the current moving through the circuit before the electrons branch. And so this would be a good way in our lab of measuring total current. Or you could measure total current here after they have all, rejoined one another, and you have all of the electrons traveling through there. You could calculate total current using this first equation that way. Or you can calculate the current through resistor 1. You can calculate the current going through resistor 2. Calculate the current going through resistor 3. It would be as easy as finding Ohm's law for each one. It's delta V over R1 is all we would need to do. Then delta V over R2, delta V over R3, and you can just add them up, because the current through each individual branch will equal the total current at both of these positions. I will do that as a demo for you so you can see it, but we don't have enough time with our hybrid schedule to be able to do that part of the experiment for you guys. So I'll do that as a demo so you can see it. You know, I'm not full of stuff, right? I'm not making this up. That is what you'll be able to notice. But I definitely want you to recognize parallel circuits can be a little bit more complicated. You have two options, equation 1 or equation 2, for calculating current in a parallel circuit, and I don't care which one you pick. I really don't. I honestly think equation number 2 is a lot easier, because calculating total resistance, that's tricky. There's the proof for it. The book gives you the proof, but this equation notoriously throws students off because you have things in the reciprocal. If I had all three of those resistors as a 10 ohm resistor, what this really turns into is 1 over x is 1 over equal to 1 over 10 plus 1 over 10 plus 1 over 10. I can simplify the whole right-hand side, sure, but I have to remember that whatever that equals is equal to 1 over x. I have not solved for x. I am not done. So take whatever that value is, put it as a fraction over 1, and cross multiply, and you're going to get x is equal to 1 over whatever that number was. And we're going to practice that no less than a dozen times. It will only show up on your exam once. In one of those scenarios, each one of these resistances will be identical, and in another scenario, they will each be unique and different. So I'm only going to ask you to do it twice. We'll practice it no less than a dozen times. You can do those practice problems way more times than that if you print out blank copies of the packets and try it again, which I've always encouraged. But that will be a sticking point. And I bring that up because on the last slide, I think using equation 2 to find the total current is easiest. If you want to use equation 1, you've got to find the total resistance through a parallel through a parallel circuit. And that equation, as you just saw, that one's tricky. So if you can find the current going through each individual resistor, you can just add those up. Call it a day. And I think that's a lot easier. A couple last vocab terms that we need to talk about. A short circuit literally is a circuit that is being made in the whole plethora of circuits you might be dealing with that is shorter than all of the others. I don't mean shorter in terms of distance. What we mean with a short circuit is you have a new circuit that has been established with almost no electrical resistance. And as we just talked about, electrons follow the path of least resistance. So if those electrons follow the path of least resistance, your new circuit with a lot less resistance, that is a lot of electrons that are going to choose that path. I say choose like they're sentient. They're not. Statistically, you will have a lot more electrons traveling through that low resistance path. Hopefully, that wasn't you putting your keys in an outlet. That's why we have those little covers at my house over the outlets for my child so that she doesn't like put a fork or our keys in the outlets, because that would be a circuit that is a lot less electrically resistant, and she would be part of that circuit. I don't want that to happen to her. So we cover them. So that's our short circuit. Another one is a fuse. A fuse is a piece of metal that we intentionally put in a circuit that is not made of copper. It's usually made of other metals that have really low melting points. Low melting points because as electrical current moves through wire, it can heat up. It's why my PlayStation gets really, really, really hot. And as it heats up, if you have more current going through it, the hotter it's going to be. It reaches a point where if you have too much current, that piece of metal will actually melt. You'll reach the melting point of the metal, and you want it to reach the melting point of the metal. The goal of a fuse is to melt before there's too much current going through your circuit and it could spark an electrical fire, or, you know, not as bad, ruin your electronics. But the goal is to prevent electrical fires. And that's what your fuses do. Nowadays, we use circuit breakers that open. It's an automatic switch that opens the circuit like a light switch. You just don't have to be there to do it yourself. It happens automatically. But it's the same idea as a fuse. If too much current is moving through the circuit, it will automatically flip a switch and turn itself off and prevent that current from continuing to move. You might have to replace the fuse. You might have to go down in the basement and flip the circuit breaker back into the on position to reestablish electrical current to whatever part of your home that it is you're dealing with. But that's what those terms represent. That was it. That's the notes. That was the whole unit all at once. I understand that was a lot. If you're still watching, props. Congratulations. Remember, come back to this whenever it is you can. And please, 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 please do not hesitate to reach out with questions or concerns. I know that was a lot. I hope we took this over little pieces. And yeah, let me know if I can help. As always, I'm here for you guys. Let me know.